Hey, this is Mr. Aiden. We're still in Unit 5, Analytical Applications of Differentiation, and we did the first derivative test last video. We're going to be going into a very important section, which is called the second derivative test, and then other videos, we're going to kind of put everything together. But first, let's focus on the second derivative test. So you can see right here, I have a function, f of x in red, and then its first derivative here is in blue, and then its second derivative is in green. You can see it's kind of like a to the third power on the red one, to the second power on the blue one, and then to the first power or linear on the third one. And obviously this is a first and second derivative. Now, a few things I want you to see about my first derivative that we talked about. In the first derivative, remember we were talking about the critical values. These values when that first derivative was equal to 0. And we call those critical points. Okay, and those critical points right here and right here, those told us when we hit our maximums and minimums. So that is where we hit our local max, and that's where we hit our local min. And how do we know those were local maxes and local mins? Is those critical values, if it goes from a positive value to a negative value, what that means is the slopes are positive over here and then to negative over here. That tells us that we have a local max. Okay, or a relative max. If we go from negative values to positive values, which means negative slopes to positive slopes, that would give me a minimum, a local minimum value. And those were our critical values. When we set that equal to 0 or undefined, that's when we had what's called our critical points. Now we're going to do our second derivative test. And if we take a look at our second derivative test, when we take our second derivative and we set that equal to 0, what happens? What happens? Well, we get this point right here. And this point right here at about 3 or so is this point right about here on my original graph. Now, what is this telling us? What is this telling us? Well, if the second derivative is less than 0, what that means is my original graph was concave down. You can see if my values are in the negative, that means my graph is showing a concave down structure. Okay, and remember, a concave down is kind of like that sad face, that negative acceleration that we've talked about in physics. If you had me in physics before, if you watched my physics videos, and that is our negative acceleration. Okay, if those f double prime, our second derivative, is greater than 0, that's going to give us a concave up graph. Okay, concave up graph. And so you can see over here, this is where we have our concave up. Our concave up is everywhere after 3 here because we're in our positive region. Well, anytime that we switch from negative to positive or positive to negative, we have what's called an inflection point. And you can see where it hits 0 is our inflection point. Where it hits 0 is our inflection point. And what an inflection point is an inflection point is where a graph goes from concave down to concave up, or vice versa, concave up to concave down. And so you can see how the second derivative test is really, really, really important to show concavity. Whereas the first derivative test really shows maxes and mins. The second derivative test shows us concavity. And so each has a tool that helps to tell us something about our original graph. So let me just give you an example on something like this. Let's say we have a graph that that kind of looks like this. And we're going to kind of come down and up and then down. That's a beautiful graph. Look at that graph. It's so beautiful. Well, let's say they give us some stipulations. Let's say the f prime of x is greater than 0 and f double prime of x is less than 0. Okay, and we have our graph here. Now, this is our original f of x graph. Now, what section of the graph are we looking at here? Well, this right here in the second derivative test says it's less than 0. That means we are looking at concave down. The only section that is concave down is from here to here. You can see we are concave down in this entire stretch, or concave ugly, either one. Well, what is the f prime of x telling us is that the slopes are positive. The slopes are going up. So here's all my slopes are going up till this critical value right here. So the stipulation of f prime of x is greater than 0 and f double prime is less than 0 is this area, is this function right here between approximately 0 and 2. Okay, so that is an example of a type of second derivative example. Another one is, let's say they give us our function. They give us our function of f of x equals negative x to the fourth plus 6x squared minus 2x minus 3. What's the first thing we do? We take our derivative. We use the power rule. We got negative 4x cubed plus 12x minus 2. And we're going to set that equal to 0. We're going to set that equal to 0. So if you think about this, if we set this equal to 0, you put that in your calculator. If you put this in your calculator, you will find out, use the solve function. Well, you can use the first derivative function if you want, or just take the power rule. Use the solve function. Go solve of this function is equal to 0, comma x in your calculator, in your TI Inspire, and you would end up finding x equals negative 1.8. X is equal to 0.17 and x is equal to 1.64. And so we can figure out what is happening there. Now, of course, we're going to take a look at these. X is equal to negative 1.8, x is equal to 0.17, and x is equal to 1.64. And we're going to test using the first derivative, using this blue function right here. We're going to test some values. If we test lower than negative 1.8, say negative 2, and we plug that right in, we're going to get positive values. If we plug in 0, we get a negative value. We get like negative 2. If we plug in greater than 0.17, less than 1.64, that's like x is equal to 1. Put in 1 in here, you're going to get positive values. You put in a number like 2, and we would end up getting negative values. So what do we know? We're going from positive slopes to negative slopes, which means this guy is a relative max. We're going from negative slopes to positive slopes, which means that's a min. We're going positive, negative, which means this is a max. And that is your first derivative test, Now let's go to our second derivative test. And so we're going to take f prime prime of x. We're going to do the power rule again. Negative 12x squared plus 12, okay, which ends up being negative 12 times x squared minus 1. Okay, so what are our values for 0 here when we set this equal to 0? Well, x can equal negative 1 or x can equal positive 1, plus or minus 1 in that x squared minus 1. So now we know these values. We know x is equal to negative 1. We know x is equal to positive 1. And now we're going to take and we're going to plug in numbers, a number less than negative 1, so like negative 2, and we end up getting a negative value. And then we have over here, you can see over here, we're going to plug in 0. We end up getting a positive value. We plug in greater than 1 into my second derivative function, and we get negative, which means this is going to be concave down. This is going to be concave up. This is going to be concave down. Concave down. Now, this can help me sketch my graph. I know all of these values. I know I'm going to be concave down at less than 1. And I know I'm going to hit a max at negative 1.8. A max at negative 1.8. Now, what does that look like if we're concave down? Okay, remember concave down is this function that looks like this. Okay, now if we're going to hit a max, we're going to hit a max at negative 1.8, and then we're going to be concave down. That means at 1.8, that will be kind of our max. So we got negative 1, we got negative 2, we got 1, we got 2. So at negative 1.8, we hit a max, don't we? Okay, and then you can see our function is going to, at negative 1, now start. We have an inflection point here at negative 1. That's an inflection point. We're going to start being concave up again. Now we hit a relative min at 0.17. So we're going to be concave up. We hit our relative min right here at 0.17. And then we start becoming we still are concave up, and you can see how we're going to be concave up all the way to about 1 or so, and then we start being concave down again, which means we have another inflection point where we're going from concave up to concave down. We hit a max at 1.64, which means we hit a max right here, and then we're going to start going back down. And this is just a quick sketch of the graph. If we want to know what it really looks like, this is what it looks like. You can see how we have a max up here at negative 1.8. We got a relative min right here at 0.17 or whatever, and we got a max right here. You can see we're concave down. We have an inflection point right here at negative 1 where we become concave up. We have another inflection point at 1 where we're concave down again. So it was a pretty good graph. Okay, now obviously I can plug in a few numbers in my original function. I could find out when I plug in 0 in my original function, we're going to be crossing the y-axis at -3, which means I can move this whole graph down a little bit to -3, and I have my graph. And so first derivative test is dealing with relatives, max and mins. Second derivative test, when we set that equal to 0, that is going to tell me when I have concavity, when we are concave up, concave down, and inflection points. That's the second derivative test, guys. Do your self-assessment. I'll catch you on the flip side. See you guys. Bye.